Okay, we have started the recording as well. So was there anything here, I know, super long, but it wasn't that bad, was it? Maybe? Anything that we need to actually recap? Yeah, what do you think?
Can I see number 8, please?
Yeah, let's click it. Click it. Number 8. That one, ratio test. Yeah, so remember we got those two tests, ratio and root tests. Here they were kind enough to tell you. Ratio. Oh, you want to actually see me do it?
Sure. I struggled with.
I didn't know if you just want to look at it. Yeah. Let's take a look at it. This one's a good one. Here we are. Okay. Hold on a sec. I just have to copy this over. What's that? Scary? Okay. I'm always scared when I see that. 2n plus 1 factorial. Okay. I got it. That's what we're trying to figure out. I don't even know what the limits are. Let's go 0 to infinity. So we're going to do the ratio test. So I do the limit. Yeah, this thing here is the answer to the first thing. So that's pretty easy. It's just that stuff. Okay, so we're going to do the limit as n approaches infinity of a sub n plus 1. So plug n plus 1 into everything. Negative 7 to the n plus 1 over 2 times n plus 1 factorial all over negative 7 to the n over 2n plus 1. Whoops. Factorial. And you've got absolute value symbols around the whole thing. So that would be your first step. I know it looks ugly, but let's dispense of some of this right now. The absolute value means that all those negatives can just be positive because negative 7 to the n, if it's negative, it becomes positive when you get rid of the absolute value. So, so we'll do that. Another thing is I'm going to flip the bottom and multiply. So that's always going to be your first move with this stuff. So we have 7 to the n plus 1 over 2. Let me multiply this out. 2n plus 2 plus 1, which is 2n plus 3. So just in case you see this is the same as that. So far so good. I've just got so this is the n plus 1 thing. I've dropped the negative and I just expanded that. And I'm going to flip this one and put it over here. So over here we've got 7 to the n, and this is 2n plus 1 factorial. Yeah, the factorials tend to be a little bit more difficult because, you're not familiar with them. I'm sure you all had no problem canceling the n's, or the 7's, sorry, the 7's. So the 7's cancel. So you end up with just 7 on the top. And then let me write out, so when in doubt, write it out. This, that factorial up there, that factorial is 2n plus 1 times 2n times 2n minus 1. And then I get sick of writing, so I just type or write ... 2 times 1. That's literally what 2n plus 1 factorial is. If it was 10 factorial, it would be 10, 9, 8, 7, 6. Here it's 2n plus 1, then 2n minus 1, and so on. I'm going to do the same thing with the bottom. Yeah, these canceled with most of those. So on the bottom, all I've got is 2n plus 3 factorial, which is 2n plus 3, 2n plus 2, 2n plus 1, 2n minus 1, and then you say, hey, that's the same as what I had on the top. And now you can see that a bunch of this are going to line up and cancel, but not all of it, but most of it does cancel. Specifically, the 2n plus 1 cancels, the 2n minus 1, everything down here, and all you're left with is just the limit as n approaches infinity of 7 over 2n plus 3 times 2n plus 2, which is 0. hopefully you can do that without multiplying that out. Does that look all right? So yeah, the limit's going to be 0. And then, yeah, so this thing will converge. So that limit is 0, which is less than 1, which means the series converges. Yeah, 0 is the ideal. It's like then you're sure that it's going to converge. Anything else that we need to look at? Yeah, what do you think?
Number 10, please.
Number 10. Oh yeah, let me just double check. Is this one okay with everyone? We're all happy with number whatever this is? Yeah, let's go down to 10, see how that does. Is this a root test? I hope so. Yes, it's a root test. So now we've got one ratio test, one root test. That should do it. But if not, we can do more. So the root test, almost the same as the ratio test. You have the same end game. And the end game is you find this limit, and if the limit is less than 1, you converge. If it's greater than 1, you diverge. And if it's equal to 1, you don't know. So number 8, A sub n is just this thing right here. So I'm not even going to write it, but I will write the root test. So I'm going to do this limit, hold on a minute, of n squared plus 8, 5n squared plus 3. Okay, so here's where we are. Oh, you know what I didn't do? I should do this. There. Now it's correct. So the absolute value is just there to say if there are any negatives, make them positive. I guess if it's a negative, like -1 to the n or something. That way it gets rid of any of the alternating stuff. Okay, so we've got this. And because everything inside the parentheses are positive, I'm just going to drop those absolute value symbols. And then you can see that this to the nth power, and then you do the nth root, you end up with these things canceling. And you've got n squared plus 8 over 5n squared plus 3. Does that look all right? So this is sort of the quintessential thing that happens every single time you do the root test, is that this root will cancel with this exponent, and then you're happy. Because then you don't have that exponent there that's making things problematic. I suppose if the exponent was there, you'd have to use logarithmic techniques to find that limit, and I don't want to have to go there, if that's all right. So, yeah, you'd have to use L'Hopital's rule with a logarithm. So this just makes it a lot easier. And then, let's see, what's left? Oh, this is just 1/5, isn't it? So then this thing is less than 1, and so you have the convergent thing. Converge. Is that all right? All right, excellent. So that one converges. All right, we happy with our, I should have had a quiz today. See, I didn't have a quiz, so we ended up a couple minutes early in Calc 1, because I guess I thought it's been too long since we had class, and I didn't want to, I should have had a quiz. I'll do one tomorrow, don't worry. So do we have anything else? Other favorites that we can slow us down? We're okay? Yeah?
I think it's number like 11 or something. It has that one.
This one?
Yeah.
Right there?
Yeah.
You don't like that 2 there?
Not much. Well, mine was higher than 2.
Okay, well, whatever it is, it's going to be red. Okay, yeah, let's just briefly mention that, because how do you do this? I'll put this down. I'll do this one. Well, I won't do it in full. The main issue is what to do at this point. So you can get to this point, of course. Oh, I guess that becomes positive, because you're dealing with a absolute value. So how do we deal with this? Okay, so what we do is we remember the rules of exponents. I've been glossing them over, just saying, oh, the exponent cancels with the root. But in reality, here's the rules of exponents. Let's apply the rules of exponents carefully. That nth root is actually an exponent, 1 over n. So we've got that. And then the rules of exponents say that when you have exponents that are nested like this, what you end up with is you end up with the product of the 2 exponents. So 6n over n plus 1 to the 2n over n. So back here, we just had the nth power, and then this is 1 over n power. And when you multiply n times 1 over n, you get 1. So that's why this ends up just being 1 here. But I've been a little bit too flippant with my exponents that I should be a little bit more careful. So what really happens is this turns into that. And now you probably see exactly what's going to happen. Here you're going to end up with the limit as n approaches infinity of 6n over n plus 1 quantity squared. And the easiest way to do this is just to do the limit inside the parentheses and then square it, which is totally legal. So with mine, it was 36. If you had a higher power than that, whatever. Let's do that. So there it is. Anything else that was a problem? I don't want to force you to ask questions, because I'm happy to move on. Because look what's coming. Power, power, power. Okay. Is that like the monster truck thing? Yeah, I need Joe Reinhardt to come and say it, then it'll sound like it should. All right, we're moving on then. If no one's got any questions about this, let's see, close this, pull this up. No, not mean value theorem. We don't want the mean value theorem. We don't want the fundamental, you love the fundamental theorem. Just a minute. Going away. Where is it? Power. Here we are. Boom. Okay, so we're doing power series. Let me explain briefly where the rest of the course, where we're heading. What our goal is, we're coming back to calculus. Not that we haven't done calculus so far, but this is weird stuff, isn't it? This series and all that junk. So what we're going to be doing is we're going to be coming back to maybe even pre-calculus, where you think of functions. So we're finally going to have x again. So we took a hiatus from x. Now we're coming back to x. So for example, f of x is equal to x cubed. That is a function. Great. And you can talk about the domain of that function is going to be all real numbers. Easy enough. Let me do another one just so that you understand where I'm heading with this. What about this? F of x is equal to, we'll do square root of x? Yeah, that'll be fun. Do square root of x. Domain. All right. There. I know we're going back to pre-calc class, but let's see how we do. Find this, find your people. So make sure you can answer that question. What's the domain of square root of x? Calc 2, here we are. Julia, you know the domain of square root of x, don't you? What are you allowed to plug into this? What are you not allowed to plug in? Negative numbers are bad. Positive numbers are good. The domain is the stuff that's good. So the domain is this. X has to be bigger than or equal to 0. So far so good? Yeah, we're doing good. Okay, let's do, let's see. Do two more. How about this one? What if f of x is equal to the secant of x? You know it. We're pulling that out. Domain. All right, does anyone know the domain of the secant function? Secant of x? See that we got Owen's doing some mental trigonometry, and then anyone else doing the mental trig? I think Haven's doing some Google trigonometry. No, it's okay. You can Google it. That's another one. Domain of secant. I could pick a volunteer at random, but I suspect that unlike most of my questions, probably not everyone wants to answer this one. Yeah, that's why I do the randomizer, because I know everyone wants to answer. I figure you're like elementary school. Pick me. This just helps. No, no one's got domain? Oh, you got it, Lucas? Oh, I like it, I like it. So I'll write this down. It's not quite right, but I like it. Negative pi over 2. So Lucas is right that there's something special about those negative pi over 2 and pi over 2. And specifically, if you plug pi over 2 into secant on your calculator, you can try this, it'll say error. Same thing goes with negative pi over 2. None like it. And the reason is that secant is 1 over cosine, and cosine is 0 at pi over 2 and negative pi over 2. So technically, that's only part of the domain, because the domain, it repeats. And so you go over a little bit, and you can evaluate this between negative pi over 2 and 3 pi over 2. And then from 3 pi over 2 to 5 pi over 2. So you can kind of see this thing repeats itself. But I like it. This is good. Okay, one more function. Let's try this. Okay, I'm getting sick of writing, so I'm going to put dots there. But what I'm talking about here is this. Brand new idea is taking a series and turning it into a function. That's what power series are all about, but I'll bet this is like a little preview of this particular series. This is going to be one of the most important series that we're going to be dealing with. And so let's just get it out of the way right now. I think you know the domain of this series. And you may not realize you know it, but once someone figures it out, you'll all be like, oh, that is the domain. So does anyone know offhand? Once again, I don't want to put anyone on the spot this time, because I'm not sure that everyone's like dying to answer. But I could give you a hint, but I suspect someone here has an idea. Do you recognize this series? All right, I'll give you a hint. Once I give you the hint, okay, now do you know the domain? You don't? Do you know what this is called? Oh, no, this is the other one. It's geometric, isn't it? This is the geometric series, and you know when the geometric series converges. It converges, well, what is it? What does R have to be? Between 1 and negative 1. And so there, R has to be between 1 and negative 1 for this to converge. And so this means that this has a domain between x is between 1 and negative 1. So that function there that goes on forever, it actually has a domain between 1 and negative 1. Anyway, that's the very first power series, and in fact, that's going to be one of the most important power series. This geometric series is a power series. It has a domain, and we're going to be referring back to this function over and over again over the next 2 weeks. So we'll come back to that, though. So let's get the boring stuff out of the way. Power series is any series that looks like this, where the c's there are just numbers. They could be any number. So those are the coefficients, are the values, the c's. So let me just see, is this important down here? No, I don't care about that. So let me just show you an example of what you might have for your values for c. Let's take a look at this. Oh, what am I doing? That was dumb. Just a minute. Here. I was, yeah. Okay, so here. Let me start again. Here's an example of a function that we're going to be studying a little later on next week. So there's C0 is 1. C1 is also 1. C2 is 1/2. C3 is 1/6. C4 is 1/24th. And if you're not sure what this sequence of numbers is, I'll tell you. 1 over n factorial, x to the n. So this particular power series, this is going to be 1 over n factorial, x to the n. Could be written like this. And this particular power series is a pretty special power series because this power series has a domain of all real numbers. We'll be able to prove that later, or see why it is. Yeah, prove. That sounds scary, doesn't it? But anyway, we'll see why that is next week, maybe later this week. Anyway, that has a domain of all real numbers, and not only that, I have another name for this function. I think I may have shared this one with you before because it's so exciting. But this particular function has another name, and that name is e to the x. So this is the power series for the function e to the x. So when we talk about a power series, we're just trying to get a representation of a function, or maybe it's just a function that has these weird coefficients. But the end goal, just so you know, the end goal is to be able to take a function such as e to the x, represent it like a power series, and then do things with this. You might say, well, what would we do with this? You don't like that? Okay, let me try to at least give you an example of why we care, since Owen is not liking this at all. And I understand. This stuff is, this is hard to wrap your head around. Let me do this. So let me ask you this. Do you know the antiderivative? Oh, if I can get my thing to zoom in. Okay, do we know the antiderivative of e to the x squared? Yeah, you know what that is, right? Oh, no, you don't know what it is because there is no elementary function antiderivative for this. Sadly, you can try. You can use Symbolab or Wolfram Alpha or whatever. You go online and see if you can find the antiderivative of e to the x squared. It's not going to happen. But what you can do is you can take this power series and just put a 2 here, and then that'll make that 2, that'll make that 4, that'll make this 6, this will become 8, etc. You see what I'm doing here? This will be 2n instead of, whoops, whatever. Anyway, so you've changed the exponents, and then you can do the antiderivative of that, which is also yucky, but at least it has purpose in its yuckiness. See, heretofore, you didn't have any way of finding this antiderivative. But now we have a method. We can write it as a series, do the antiderivative of the series. We still won't have a nice elementary concise form for it, but at least we'll have an expression for the antiderivative. Okay, yeah, you guys are losing your minds, I know. Owen is just the only one who is willing to express himself. Thank you for being expressive, Owen, because everyone feels that way. I feel that way. So thank you. Anyway, but we're going to do this. We're going to get her done here. So we've already talked about this power series. That's the geometric power series, and we've talked about convergence and divergence of that power series. So anyway, the idea of convergence, divergence has to do with the fact that this thing is the geometric series. And so as long as x is between -1 and 1, this thing will converge, and it will diverge otherwise. Okay, so that's going to be sort of the basis for the rest of these, at least for now. So let's take a look. What is the sum? Well, yeah, let's go ahead and do this. Do you know what f of 1/2 is for this? So f of, here, I should say, here is the function that I'm calling f of x. There it is. So can you compute for me f of 1/2? So see if you can do that. And I'm going to see if I can find my graph of this particular power series, because this is fascinating. Let's see, open. Okay. Haven't got my, oh. That's better. All right, I'll have to fix that in a minute. Let's see how we did. So I just want to know if you know how to add up this geometric series. I'll bet you do. In fact, Raylan knows what she's doing with this one. What's f of 1/2 for this thing? What's the sum wherein goes from 0 to infinity of 1/2 to the end? Okay, yeah, I know. You want to write this down first, and I appreciate you looking out for your friends here. So let's do this so that we can remember. Do you remember the formula? You got a 1 here, yeah? Yeah, it's A. So it's the first term. So yeah, the way that we were always the first term divided by 1 minus the common ratio. So yeah, perfect. So that's what we're going to do for these, is that's the sum. So thank you, Raylan. Pearson, so apply that to this first one right here.
So I think it's a bit wrong, and the first term is not 1/2.
Yeah, because I'm starting at 0. But no, that's fine. You can just do the quick correction here.
2.
Yeah, it's going to be 2. So it's 1 over 1 minus 1/2, which is equal to 2. So that one does converge to 2. All right, what about this next one? Let's see, can we apply this to the next one? You're not here, but Gina is. Gina, what do you think of that next one?
Well, it's going to not have, it's going to diverge because R is divergent.
Yes, so if you try plugging things into this, you'll get a number, but that number's not going to be right because this one diverges. And the reason this diverges is because this thing is only, here it is, it only converges between -1 and 1, and it diverges otherwise. So there you go. So sometimes you can use this formula, sometimes you can't. The interesting thing is that it turns out that this formula, which I'm just going to write like this, 1 minus x, is actually equal to the sum of r to the n, oh, not r to the n, x to the n. All right, change that to an x. This should be x to the n, and this is when -1 is less than x is less than 1. So those two are exactly the same. Yeah, what do you think, Briar?
So the f of 1/2 and the f of 2, is that just telling us the ratio?
Yes, in a sense. So here, what we did was we defined f of x to be this. And so if I asked you what is f of 1/3, you would say, oh, f of 1/3 happens to be this. So it's just, I'm just taking a series and I'm treating it as if it were a function. So this function is defined as that series. Yeah, this is hard stuff. I remember it was painful, and in fact it wasn't, I gotta be honest with you, it wasn't until grad school that I started seeing, oh yeah, I see the connections now. So do your best and play the game, I guess. Think of it as a game and a puzzle. But anyway, I wanted to show you the picture. Let me just fix this because I don't like my limits here. Let's see, we're going to go from negative 0.9 to, hold on a sec, 1.1. Okay, I have some graphs I'd like to show, and this will be helpful, I hope. Guess we're going to find out. Negative 1 to 1, crud. Sorry, let me try again. Negative 1 to 1. Almost there. You'd think I could figure this out. Should have had it set up ahead of time. Yeah, I'll show you this in just a sec. You'll see. Hopefully it'll be worth it. And then there. And then there. And done. Whoops. Why? Sorry, uh-oh. Okay, finally, it got what I wanted. Okay, let me put this up there. Make it bigger, way too big, smaller. There it is. Okay, so here it is. Sorry it took me so long to get this. Whoops, now it's too small. Now it's big. Maybe a little bit smaller. Okay, that's good. Okay, so here what I've got, just to explain. What do I have here? Oh, I know what I've got. So what I have here is this is the graph of 1 over 1 minus x between negative 1 and positive 1. So I know you got that vertical asymptote there for positive 1, but just ignore that for now. So this is the graph, f of x is equal to 1 over 1 minus x, in red here. The black line there is just 1. F of x equals 1. And then, so what I'm going to do is I'm going to go through a series of, what is it called, like different functions, and basically they're just going to be it's going to be 1 and then 1 plus x, then 1 plus x squared, 1 plus x cubed, and so on. And that's what's going to be black here. Just to demonstrate what the Taylor, or no, we're not going to name it yet. Let's see, do I do this? I think this is what I click. Yeah, there, that's 1 plus x. I know it looks like it's not got a slope of 1, but that's okay. This is 1 plus x squared, 1 plus x cubed, x to the 4th, x to the 5th, x to the 6th, x to the 7th, x to the 8th. You'll notice that it lines up almost perfectly between negative 1 and 1. It's just this little tail here, and you can't see what's going on over there, but you have a similar problem over here. But anyway, if we keep going, let's see, oh, well, I guess it looped around. I only have 20 or so of these. So eventually, okay, it loops around. Let me go back. So this is the biggest one I have. So these two functions, this is the sum of 1 plus x squared all the way up to x to the 20th, and it almost matches up to negative 1. So if you go far enough in your series, what you get is you get a function that will match exactly the red function, which I know isn't super exciting, but we're going to do this. We're going to be able to do this for any function. This is just for this one function. This is the beginner function, which may discourage you because this seems super complicated. Okay, we've talked about this, divergent. Okay, so there's additional complications that occur when you have something like this. This is just a power series that's centered at a different point. I know the word centered and this whole, all the language is totally new, and so one of my jobs is to try to help you understand why we say this. So let's just sort of understand this for a sec, and then I'll try to explain what it means to be centered at a particular number. Ignore that. Okay, so let me show you another example of a power series. And here again, this power series is geometric. So they're not all geometric, I should say, but this one happens to be geometric. And so this one's geometric, and so we can say that this will converge when the common ratio is between -1 and 1, which in our case, the common ratio is this x minus 2. And so notice that what happens when you do the math here, you get x is between 3 and 1 is where this thing converges. If you do just add 2 to everything. And if I draw that on a number line, here's 1, here's 3, here's a number line with that. Notice that the middle of this is 2. So centered at a number just means that the convergence, where it converges, will be the middle of the convergent area will be at whatever number is in here. So that number represents where we converge. All right, I know this is overwhelming, but I want to take my time and make sure. So you're all right? What do you think, Tony?
So, but any number is between 1 and 3, not just 2.
Yes. Yeah. This is this particular series will converge for any number in between, but 2 just happens to be at the middle. Yeah. So I'm just trying to explain the lingo, so that when you see centered at, or when you see this word about a number, it just means it's centered there. Let's see, we can skip that, okay. Okay, so now here's the first one where we're asking a question about where will this thing converge? So the way we're going to figure out where something converges is we're going to use the ratio test. So it's just the way it's going to be, okay? So let's set up the ratio test, but you know the ratio test. So let me remind you of the ratio test. First things first, we write down what a sub n is, just like you did for your homework today. The second thing we're going to do is we're going to do the limit as n approaches infinity of a sub n plus 1 over a sub n. We're going to do all of this. Let's go ahead and pick some people to help me out here. Joe, what is a sub n? It is, exactly. Just like on your homework, it's whatever's in here. I know you felt like that was kind of redundant, didn't it? Didn't it feel stupid to just write down that thing that was in the summation? That's how it felt to me. But now you see, the reason is because we need to know that whole thing is that. All right, now go ahead and write down a sub n plus 1 over a sub n using that a sub n. I'll give you a minute, then you can pick a volunteer here. All right, Julia, what do you get when you do a sub n plus 1 over a sub n? Okay, so Julia's gotten us started here. N plus 1 factorial. Haven, can you finish it up for us? Yeah, so you guys might help if you had a piece of paper in front of you, so you could write it down. That's right, x to the n plus 1. Yeah, it's a good, even if you're just pretending, if you have a piece of paper, then it makes me feel like you're doing something or following along. So you could borrow if you need to. I have some up here. Okay, very good. X to the n plus 1. Let's get the bottom. Cheyenne, what do you got for the bottom there?
N factorial x to the n.
Excellent. Okay, so once again, this feels so complicated because now you have an x to the n. If you understood the ratio test, so the homework you had to do today, if you understood that, then just suspend your disbelief for a minute, ignore the fact you have an x here, and just treat the x the way you did any number in that ratio test. And it'll be okay. So we get to this point and we're like, what do we do? Just proceed carefully, slowly. Let's see, what can we do? Now, in this case, I was pretty blasé about just dropping the absolute values before, but in this case, we're going to keep the absolute values there. It's just the way it is. So I'm doing the limit, because we don't know if x is positive or negative, that's why. So the limit is n approaches infinity. We can do this, though. What do you got, Sarah? Sarah, you're up here. What do you think? Oh, tell me, I'm sorry. Let me pick something. Yeah, would you like to deal with the factorials or the x's? I'll give you your choice. Really? Awesome, I love it. Okay, tell me how to deal with those factorials.
Well, the only one that isn't canceled out would be n plus 1.
So good. She remembered. Okay, very nice. So you have n plus 1 factorial, which is n plus 1 times n minus 1 times n. On the bottom, it's n times n minus 1 times n. And so everything's going to cancel except for n plus 1. Thank you. So n plus 1, yeah, just treat it the way we did on the homework. N plus 1 over 1. We're good so far? So I've dealt with the factorials. Let's do the x's. I know, whoever gets chosen. Evan, can you handle the x's? What happens? Where? On the top, we get an x. All right, very nice. Okay, so we've got that. And we want to know what? Well, we want to know what's going to happen to this. I think we know what's going to happen to this. Let's find out. So this thing, Owen, do you know this limit? It is infinity. That equals infinity. Now let me remind you of the ratio test that you just did. The ratio test said that if you do the limit and you get a number between positive and negative 1, your series converges. If it's bigger than 1 or less than negative 1, the series diverges. So this one diverges. Everywhere? Question mark? There's actually one place. What do you think?
Isn't the ratio test just when it's less than 1?
Mm-hmm. Yeah, so this is this less than 1? Oh, yeah. I dropped that. If you think of the absolute value there.
If it's between negative 1 and 1, then it's converges. But
Yeah.
isn't it just anything less than 1 converges?
Yeah, well, with the absolute value there, you're right. Less than 1, it will converge. Bigger than 1, it diverges. So this thing will diverge for sure. Question is, everywhere? Does it diverge everywhere? No matter what x is? Is there anything you can plug in here that will make this not diverge? Yeah, 0. 0 is the only thing. See, I'm saying what happens when x doesn't equal 0, but if x equals 0, this actually converges. Because this all will be 0, not infinity. So this is only when x is not 0, but when x equals 0, you actually converge. So this diverges not everywhere except for 0. So at x equals 0, this thing converges, and at x equals 0, this is boring, because at x equals 0, you have n factorial times 0 to the first. Add up all of those, you get, whoa, what do you get? Oh, I'm scared of the 0 there. You get 1. We're going to just say you get 1. So, okay, that was boring. Well, no, it wasn't boring. It was interesting. Okay, what about this one? For what values of x does this converge? So here again, we have something different. Like, how in the world are we supposed to deal with this? Well, you do the ratio test. So ratio test. So we have to figure out what is a sub n, and then you do the limit as n approaches infinity of this. And then we're going to do, I'm going to be more careful this time, Tony. So thank you for making sure that we write it all down. Because, yeah, I don't want to be flippant about this. So, Briar, what is a sub n for this one?
Just the x minus 3 to the end of
Yes. So it's just that stuff in there. That is, yes, right here. I know. Seems silly to write it down, but it's okay. Now we have to write down the ratio test. Sean, you know how to write the ratio test, don't you?
X minus 3 to the n plus 1 over the oh, wait, so, is that right?
That's the top.
And then the bottom is just x to the 3 to the n over n?
That's right. Very nice. Perfect. Okay, so like I said, Tony, I'm going to be more careful here. So you got the limit as n approaches infinity. We're still going to do the same things we did before. X minus 3 to the n plus 1 times n over n plus 1 times x minus 3 to the n. Okay. Surely we can simplify this a little bit. I know it's not gonna be great, but we can simplify it some. So what can we do here? We can cancel some stuff. Let's get you to cancel. Sydney, you can cancel, can't you? So on the top, you mean? Yeah. So we've got x minus 3 times n over n plus 1. All right, now for the hard part. We got to do this limit. Limit as n approaches infinity of this stuff. There's a trick I can show you, but I think I'd like to see if you can do it. It's not that big a deal of a trick, but I don't want to blow your mind before you actually figure it out. So, because if I show you the trick, then you're going to say, where'd that come from? And then I'll have to just do it from scratch anyway. But take a minute, see if you can do that limit. By the way, x, what is x? X, I don't know. Don't know what x is. So just, treat the x as if it were a constant for now, I guess. Oops. Well, Lucas, what do you think? X minus 3, is that what you said? Yeah, just x minus 3. Because whatever this is, if it was the number 7, then the limit would be 7 over 1, right? And if this thing was the number 12, this would be 12 over 1. If this was the number 1/2, this would be 1/2 over 1. So whatever this is, that's the limit. So in this case, that's what the limit's going to be. So this is equal to just x minus 3. Now you might say, wait a minute, what's the absolute value still there for? The reason I still have the absolute value is because I don't know what x is. And if x is, say, 4, then this will be 4 minus 3, which is 1. But if x was the number 2, then this will be 2 minus 3, which is -1. And I'll need those absolute values there. Okay, so there's what we got. So we're going back to Tony, because he's the one who brought it up the first time. When will this converge? What should I put over there? Oh, 1, yeah. This will converge as long as this thing is less than 1. So we'll get done with this, and then we'll talk about how this shakes out. Anyway, this converges when that's less than 1, which is, let's see, let's do a little bit of math here. That means this. That's what this means. So because I have an absolute value there, I can drop the absolute value as long as I include the positive and negative. And now you can do this algebra, right? Add 3 to both sides, or add 3 to all 3 sides. So you've got 2 is less than x, is less than 4. Whew. So that's when this thing converges. Now there are 2 things that we haven't dealt with, and those are the endpoints, because this thing says that this will converge here. But what happens if x minus 3 is equal to 1? For example, x equals 4. Does that converge or diverge? What about x equals 2? Does that converge or diverge? And the answer is we don't know, because when you do the ratio test, if you put x equals 4 into here, and you do the ratio test, your limit is 1, and same thing goes with this. The limit will be 1, and when the limit is 1, you don't know. And so you actually have to do the work to figure out, and I'll bet this won't take long. Watch this. So when x equals 4, I get this. And when x equals 2, I get this. All I've done is I've taken that and I've plugged x equals 4 into that, and it gives me 1 to the n over n. And when I plug x equals 2 into that, I get x minus 3 is negative 1 to the n over n. And you know when these things, so let's just ignore the x for a minute. That thing has a name, and you know if it converges or diverges. In fact, Tony, I actually randomized you this time, but that top one, you know what that's called, don't you? This one right here.
Harmonic?
Yeah, it is harmonic, so that thing diverges. Okay, whatever. Bottom one, let's see, can we do that one? Pearson. That one's called the alternating harmonic series. Do you know if that converges or diverges? It does converge. So that one converges. So you converge when x equals 2, you diverge when x equals 4. So here is what I will do is down in my answer, I change this to a less than or equal to. So that's where this thing converges. Wow, we only have 2 minutes? Come on. Let me see. Is my homework right here where I can click it? I hope so. Power series, view it. Give me a sec. I want to see the preview. Otherwise, because I don't want you to lose your... Wow, so many problems. Hold on a minute. Okay, so this... Oh, yeah, you can do that. Radius of convergence. Okay, radius of convergence. That means... so the radius of convergence is just how far from the center it converges. So this has a radius of convergence of 1. So that's what radius means. R equals 1, and this is the interval. Let's see, what else we got? Radius, interval, radius, interval, radius, interval. Are they all like that? Uh-oh, click here to begin. Oh, these start to scare me. There's some that are more complicated. See how you do. Maybe I'll just leave them alone. We'll pick up the pieces in the morning. Oh, look, it's due in the afternoon anyway, so you'll have time to pick up the pieces. So do your best, and we'll do. And I'll get a quiz for tomorrow. I'm stopping the recording.